All right, so this is Programming Concepts and Methodologies. We're going to cover the last chapter from your book today, the last chapter in this class, chapter 13 on string matching. Then I've just got some demos after this, and the next week I'm not going to have any chapters in the book. I'll probably just have more demos of projects, probably more machine learning. I haven't quite decided yet. I'll post them here. All right, so we're coming rapidly to the end. Final exam will become available later in December. All right, so let's take a look at this chapter. So string matching. We're going to talk about how it works and then 4 major algorithms for it. So the notation is simple. You have a string and you have a substring. P is the prefix of the string. The remainder is called U. Doesn't really matter, actually. We're not going to use these definitions much in how we talk about these things. This was kind of interesting. There is something called ends with and starts with in Python, which I didn't know, a way to pick parts of a string out. Sort of interesting. Anyway, so pattern matching. You have a pattern, you're looking for it in a text string. So you have BAB, so you can't be here because that's an A and it can't be here. It could be here. It's there. So you found a case, and typically you talk about running an algorithm to find all matches, but you could just have an algorithm to find the first match, and those would be simple. All right, that's the task. And of course, the simplest thing is just a brute force algorithm. What I just did there, put it in the first place, compare every element, or at least compare until you find a mismatch, then you don't really need to go any further. Then move it over 1, try again, move it over 1, try again. That's the brute force algorithm. And as should be sort of obvious, that's going to take m times n comparisons. Each location, you're going to compare it to the string is length n. You're going to compare it to each element in the string, except for a few at the end. Then this is length m. Then each one might take up to m comparisons to decide it matches or doesn't match. So obviously that's going to take something like m times n calculations. All right, that's brute force. And there you go. Compare until you hit a mismatch, then move it over by 1 and compare again, and so on. Off you go. Now, by the way, notice how stupid this is. I knew that it matched A, C, B, C, A. When I found a mismatch here, I already knew what the first 5 characters were completely. So I could have known there's no point comparing the A here or here or here or here, since I know what these characters are and I know they're not an A. So that's why this is the brute force algorithm, which is very wasteful. It does a whole bunch of repetitive comparisons that you don't need to do. And that's why all the other ones are better. So like I say, it's going to be the best case is order of n, and the worst case is order of n times n. Like that. All right. So rabbit and carp is one way to deal with that problem. And this one uses hashing. And so it's kind of crazy. I guess your hash function better be pretty fast. But what you do is you compare hashes instead of comparing strings. So that will reduce the number of comparisons, but you'll have to calculate a bunch of hashes. So your hashes would have to be faster than the comparisons, I guess. You do a hash of the pattern and of all possible substrings of the text with length m. And then you compare the hashes one by one until there's a match. That's certainly one way to do it. It is very difficult for me to understand how this could possibly be an improvement, because even a simple hash function, it seems to me, it would take a lot more compute time to calculate than a comparison, perhaps if m is very large. If you have if the thing you're matching is 100 characters long, then you'd have to do up to 100 comparisons, and doing one hash comparison might be faster then, I guess. That would be when it might make sense. Anyway, they don't talk about when you'd use this in the book. They just talk about how it works, and of course that's the thing. You have a substring here. Here's your pattern, 5 letters long. So you hash it. Then you hash every group of 5 characters from then on and see where they match. It'll work, of course. All these techniques will work. It's just not clear to me when this would really be the best. All right. Anyway, what's more like it is the KMP algorithm, named after 3 people, including the very famous Knuth. Knuth published C programming textbooks, and he famously promised $1 to anyone who would find an error anywhere in his books. And people would get those checks and frame them and put them on the wall, which I really appreciate. I've only found 2 textbook authors in my entire career who published books that didn't have any mistakes in them. And by the way, your book is not an exception. Your book has mistakes in it. I mentioned as we go by. It doesn't have too many mistakes, but it does have some mistakes. But there are a few textbook writers that actually get all the mistakes out of it, and Knuth was famously one of them. Anyway, so what you do is use the structure of the target to avoid unnecessary comparisons, like I'm saying. If you were able to compare this and you made it all the way to the 6th character before you found a mismatch, then you know exactly what the first 5 characters are. You know that if this one is A, and you know that none of these ones are A, so you might as well skip to this point. So you can skip over these 3 steps and go to the next A that matches and carry on from there. Now notice that you just compared this D to a B and observed that it did not match, and therefore, if you remembered about the B, you'd know that this C can't match, and you would be able to move it even further, but this algorithm is not smart enough to remember that value. The next one is. Anyway, so that's one way to move forward, and by the way, the figure in the book is wrong. As I mentioned, there are errors in the book. Anyway, so here's the pattern BCA, BC. So when it matches here, you've got a BC here, and a mismatch, so you move it to the next BC when it mismatches and carry on. And again, you're too stupid to realize that this was a C, and therefore the BC is not going to match there. So it is saving some time compared to brute force, but it's not completely optimized. So they do this with a thing called the prefix function. You pre-process the pattern itself to find repeated characters in the pattern. So the prefix function, if the character has never been seen before, the prefix function is 0. But if you have a repeat, then it counts how many characters in a row have been repeated. So here you have the first 3 are 0. Then you're going to have an A. And A is a repeat, so you have a 1 here. And B is another repeat, so you're going to have a 2 there. And that tells you how many characters. That tells you you can skip comparing the first 1 character if you move it to here. You already know it's going to match. You can skip comparing the first 2 characters if you shift to here, because you know it's going to match from the structure of this. So that's what this is. This helps you figure out where the next shift should be. All right, and so there's code to run it. I don't think it's really worth running. I had to get some code and run it to find the errors in your textbook. It had some figures with the wrong shift, and I just had to run the algorithm for real to get it to work. By the way, this was written by an AI. I just did a Google search and it wrote code which worked, which is pretty cool. Anyway, when you run it here on this data, you can I've added some print statements to print all the comparisons. So it compares A, C, B, C, and match, 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 and another A, and then D is the mismatch. And after that, next comparison it does is to compare the 4th element to text 4. Pattern 5 to text 5. Pattern 1 to text 5, that's what you do. So 1, 2, 3, 4, 5, you move it to here. That's why this diagram is correct. I think I had to modify the text in the diagram in your book to make this correct, but I figured it was correct by running the actual algorithm. Anyway, that's how it goes. That's the KMP algorithm, which is a big step up from brute force. The Boyer-Moore algorithm saves even more time, but it is more complex. And what it does is you're going to shift the pattern from left to right, like you did, but you're going to compare from right to left. And you're going to skip unnecessary comparisons by using 2 heuristics, good suffix and bad character. And what they're like that prefix function we saw before. They tell it how many comparisons you don't need to make. Let me check for comments in the Twitch, by the way. There are no new comments. Okay, all right. So, all right, so that's bad character and good suffix heuristics is what you're going to do. You're going to run both of these algorithms and choose the largest possible shift. Both of them exclude certain shifts as being unnecessary. So now here you have BCA, BCB, and you mismatch with the D here. And like I say, the previous algorithm was so stupid it would not notice that this D is not anywhere, but now this one is going to notice D is not in the pattern. Therefore, since there's no D in here at all, you don't need to bother with any shift that would have any part of it. You have to go right past it. If you're going to match it, it would have to be after the D. So you can skip by the whole length of the pattern, which is 6 in this case. All right. This time you have a bunch of matches, and then you have a mismatch, but this is A, so you shift it to where an A hits there. Where you know all these previous characters match, and there's an A, and then you can keep checking. So that's the idea. So the bad character heuristic, if the mismatched character does not occur, then you go all the way past it. If the mismatched character has 1 occurrence, then you align with it. If the mismatched character has more than 1 occurrence, then you make the smallest shift possible. And you'll see that here. So here we go. We have AC, AD, and we're trying to hit AC. So here we have a mismatch. Now, the D does not appear anywhere in the pattern, so we go to the right of it. That's the mismatch character. It doesn't occur in the pattern. That's the first case. And here's the other case. You have pattern is AC, AAAC, and we're looking for AC. So when you fit the fourth character, the A doesn't match the C, but there is an A. So you could move it to where this A hits that A or where that A hits that A. And clearly, you have to take the smaller of them because you only know about these characters. Really, the only thing you know in this case is the A. So you cannot exclude this possibility. You're going to have to take the smaller shift and test it before you go to the larger shift. So that's the game. You just take every previous occurrence of that character, which the previous algorithm ignored, and try shifting it by the smallest amount necessary to make that character line up again. All right, that's the bad character heuristic. Now the good suffix is where you match from the end and you find one or more occurrences in the pattern. By the way, it occurred to me my explanation here is probably wrong because you do compare from the right, not from the left. So you compared here CA and an A appeared there. So you know that this is an AAC. And that's what kind of confuses me about this one. This seems to have another kind of stupidity. Since you started comparing from here, you knew that this was a C and an A. Therefore, you know that both of these are wrong. And yet you do it. So again, it doesn't seem completely perfect to me. But anyway, that's the game. All right, the good suffix is where you have a suffix that matches. So you start comparing from here, C, A, B, and a bad match there. So you shift to match the other occurrence of the AC. Match the AC here. All right, just another way to do it. And the point is, so here you go, CAA. She matched to the other CA. There's two of them, CA and CA, and of course you have to use the smallest shift. This one might match. So that's the game. All right, and I'm not going to work through the details of the other examples. I think it just gets a little mind-boggling. The point is, it's another way to avoid doing unnecessary comparisons. And so in the book, they say it's order M for pre-processing the pattern, and in the worst case, MN. But I went and looked online, because if it really was order MN, there'd be no reason to use it at all. The brute force algorithm is order of MN. Online, they say there's an optimization called the Galley rule you can add to it, and then it's linear in all cases, which means order of N. So anyway, that's why this is the most popular one. So brute force is simple but inefficient. Rabin Cart uses hashing, and it seems like a little hard to understand when that would help. Yeah?
I was doing a little bit of research, trying to figure out why Rabin Cart is more efficient.
Yeah.
And from what I can gather, it's mainly because it uses a rolling hash, so it doesn't do everything from scratch every time.
Oh, if it finds repeated characters, it already has a hash pre-calculated?
Yeah.
Okay, but then it has to do comparisons to verify the repeated characters. Yeah, but anyway, that would help.
That, and I think it's just easier for the computer in practice, just because instead of having to go through all the substrings, since, in code like C, the strings have it corresponding to a bunch of characters. So instead of comparing all that, you're just comparing numeric hashes.
Yeah, but you do have to process all those characters to compute the hashes. So I mean, I'd have to see it. I mean, it wouldn't bother talking about it if it didn't have some advantage.
Apparently, the time complexity is exactly the same, like the worst case time complexity. It's just that it's faster in practice.
Yeah, I can believe that. I mean, there must be some case in which it's valuable. Anyway, so this uses the hashing. Then KMP uses overlapping substrings in the pattern, and Bayer-Moore, as we saw, uses information about the mismatched characters in the text. And this is the most popular and apparently the most efficient in practice. That's the default, the Boyer-Moore. All right, so let's try some Kahoots. This is chapter 13, the last one. What's that? Okay. It's optional. Oh yeah, laptop or cell phone is necessary. Yep, yep. That makes sense. There's always some people that prefer not to do it. All right. All right, so which one shifts the pattern by one character after every mismatch? Yep, that's brute force. Not a popular answer, but that's the one you can always do better than that. Move 15 over by one character every time is the stupidest possible algorithm. And that's brute force, where you do a whole lot of unnecessary work. All right, which one calculates hash values? That's the rabbit cart. All right. All right, which is the most popular? Boy or more. That's the most modern one. All right. Okay. So. What's that? Yeah, only 3. Yeah. Yep. Sometimes I write 3, sometimes 4. All right. So let me check for comments in the Twitch. There are no new ones. All right, so I'm going to stop this recording.